Hello, in this lecture we'll answer two questions. In the first question we'll find out the area of this green shape, and in the second question we'll find out the length of line segment PQ is equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing we have a circle inside this big semicircle. We also know that this is line segment AQ, that is equals to 4 units in its length. This is line segment TB, that is equals to 1 unit in its length. This is angle STB, that is right angle. This is angle PQA, that is also right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x and the radius of this small circle as y. And we define the center of this small circle, this point is point O, and the center of this big semicircle, this point is point C. In addition, we will define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent ST with this small circle, this point is point L. We define the point of tendency of tangent PQ with this small circle, this point is point H. And finally, we define the touching point of this small circle with this big semicircle. This point is point K. In the next step, we will join points O and N together by a straight line. Point O is the center of this small circle, point N is the point of the small circle itself. Therefore, ON is the radius of this small circle, that is equals to y according to our definition. The radius ON that is equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This is angle PQA, that is a right angle. AB is the diameter of this semicircle. So AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB, it's point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, we will focus on the upper side of the straight line AB at point T. Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T? We have this angle, that is right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, We join points O and L together by a straight line. OL is of course the radius of this small circle. This is equals to Y. The radius OL is known to point L. That is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it is that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. So inside quadrangle OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle OLTN, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at least rectangle if not a square. So in relation to quadrangle OLTN, it's a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side NT. But OL is Y, therefore the opposite side NT must be also equal to Y units in its length. In the next step, we join points O and N together by a straight line. OH is of course the radius of this small circle, that is equal to Y. The radius OH that is equal to Y, the radius OH is known to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in quadrangle HO and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle HO and Q, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if not a square. So in that quadrangle HO and Q is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle HO and Q, side HO must be equal to the opposite side QN. But HO is Y, therefore the opposite side QN must be also equal to Y units in its length. This is line 7 QT. Line 7 QT is a straight line because it is part of the big straight line AB. Part of a straight line must be also a straight line. So QT is a straight line. Therefore QT in total must be equal to QN plus NT. This is to say QT equals to Y plus Y, that is 2Y. AB is the diameter of this big semicircle. Therefore, it is twice as long as the radius. The radius of the semicircle is x, therefore the diameter must be equal to 2x. So I write it down. The diameter AB of the semicircle is equal to 2x from one side, but from the other side, AB equals to AQ plus QT plus TB. Again, AB total equals to AQ plus QT plus TB. So I write it down. AB equals to AQ plus QT plus TB. So AB is equals to 2x is equal to AQ. AQ is 4 plus QT. We just write down from there that QT equals to 2y units in its length plus TB. TB equals to 1 unit in its length. So in total, if we found out that 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, and 4 plus 1 is 5. So 2x equals to 2y plus 5. Here we subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we take 2 as a common factor from those two expressions, and we get that inside the brackets we have x minus y equals to 5. So 2 times x minus y equals to 5. Here we divide this equation by 2, and finally get that x minus y equals to 5 over 2 units in its length. 5 over 2 is 2.5. So in total we should find out that x minus y equals to 2.5. What is the length of this 9797 cm? For the long, it is very easy to see that cn in total equals to CB minus nt minus TB. Again, cn equals to CB minus nt minus TB. So I write it down. Cn equals to CB minus nt minus TB. Again, Cn in total equals to CB minus nt minus TB. So Cn equals to CB. CB is the radius of this semicircle. Is equals to x minus nt. Nt equals to y minus TB. TB equals to 1. So in total, if you found out that Cn equals to x minus y minus 1. So Cn equals to x minus y is 2.5. So instead of x minus y by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, if you found out that Cn equals to 1.5 units in its length. Okay. This is 97 Cn is equal to 1.5 units in its length. So we have in the drawing an internal notch between this small circle and this big semicircle. That is to say, they touch each other internally at this point, point K. Whenever you have an internal arch between two circles or semicircles, you can implement rule 9. So you can repeat quickly on rule 9 and we'll implement rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects the centers together passes through the attaching point. So in the drawing we have two circles. The center of this big circle is here at point O. The center of this small circle is here at point M. The straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through the attaching point at this point P. Again, the straight line OM must pass through point P, that is the attaching point. Or OMP is one straight line. Again, according to this rule 9, OMP is one straight line. So we can implement rule 9 in our drawing. Well, in our drawing, we have an internal arch between this small circle and this big semicircle at point K. The center of this big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects the centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through the attaching point at point K. Again, according to rule 9, the straight line CO must pass through point K, that is the attaching point. Or COK is one straight line. Again, COK is one straight line according to rule 9. So we join point C altogether by straight line. And the straight line CO must pass through point K, that is the attaching point according to rule 9. You can see from the drawing that the straight line CO passes from point K, that is the attaching point exactly like rule 9. Exactly according to rule 9. So if COK is one straight line, it means that CO must be equal to CK minus OK. So write it down. Actually found out that CO equals to CK minus OK. So CO in total equals to CK. CK is the radius of this semicircle. That is equals to X minus OK. OK is the radius of this small circle. That is equals to Y. So in total, we found out that CO equals to X minus Y. CO equals to X minus Y. So this is line segment CO that is equals to X minus Y, and it's in its length. But we already found out that X minus Y equals to 2.5. So CO that is equals to X minus Y, it is equals to 2.5 units in its length. In the next step, I'll copy the right triangle OCN in a new page and we'll implement the Pythagoras theorem on this right triangle OCN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Line segment CN equals to 1.5 units in its length. Or side CN equals to 1.5 units in its length. Side ON equals to Y, it is the radius of the small circle. and the hypotenuse also equals to 2.5 units in its length. Here by PT is a relation for Pythagoras theorem. So actually this is the right triangle OCN that I got from the original drawing. This right triangle OCN, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. OC equals to 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it equals to ON squared. ON is y, therefore ON squared is y squared plus Cn squared. Cn equals to 1.5 units in its length, therefore Cn squared equals to 1.5 squared, that is 2.25. So in total we found out that 6.25 equals to y squared plus 2.25. Here we will subtract 2.25 from this equation, and you get that 6.25 plus 2.25 is 4, so 4 equals to y squared. Here we take a root out of this equation, and finally you get that y equals to the square root of 4, that is 2. So if you found out that the radius of the small circle y is equals to 2 units in its length. We have already found out that x minus y equals to 2.5. Y is 2, therefore x minus y is x minus 2. That equals to 2.5. Here we add 2 to this equation, and we get that x equals to 2.5 plus 2 is 4.5. 4.5 is 9 over 2. So if you found out that the radius x of the big semicircle is equal to either 9 over 2 units in its length, or in terms of numbers, the radius x of the big semicircle equals to 4.5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the big semicircle minus the area of the small circle. So write it down, the area of the green shape equals to the area of the big semicircle minus the area of the small circle. So what is the area of the big semicircle? We know that the radius of the big semicircle equals to x, therefore the area of the big semicircle must be equal to pi x squared over 2 minus the area of the small circle. The radius of the small circle is y, therefore the area of the small circle must be equal to pi y squared. So in total, if you found out that the area of the green shape equals to pi x squared over 2 minus pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total, this expression equals to pi over 2 times 9 over 2 squared minus pi times y squared. Y is 2, therefore y squared is 2 squared. Therefore y squared is 2 squared, that is 4. So this expression in total equals to 4 pi. So if you found out that the differential equals to pi times 9 over 2 squared minus 4 pi. We'll open the brackets of this expression and we get that we have here pi over 2 and 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4, minus 4 pi. So this expression in total equals to 81 pi over 2 times 4. 2 times 4 is 8. So if you found out that the area of the big semicircle equals to 81 pi over 8 square units in its size. Minus the area of the circle, that is minus 4 pi. So here we multiply minus 4 pi by 8 and then we divide it by 8 in order to overcome factor with this expression. And we get that minus 4 pi times 8 is minus 32 pi over 8. 81 pi minus 32 pi is 49 pi over 8. 49 pi over 8 is equal to 19.24 square units in its size. So if you found out that the area that you are looking for in this question, that is the area of this grain shape, it is equal to either 49 pi over 8 square units in its size, or in terms of numbers, is equal to 19.24 square units in its size. So we finish the first question. In the next step, I'll present you the second question and we'll answer the second question of this lecture. Our task in the second question is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the domain we have a semicircle. It's given us the question that point O is the center of this semicircle. This is angle PTS, that is right angle. This is angle PQB, that is also right angle. This is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. And it is given us the question that line segment PT equals to line segment TS in its length. So if we define the length of line segment PT as A, then the length of line segment TS must be also equals to 1 units in its length because they are equal to each other. In the next step, we will complete this semicircle to a circle. We completed the semicircle to a circle, and we will extend line segment TS by a straight line until it touches the circle. And we will define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we'll join points M and P together by a straight line. By doing all those constructions, we created peripheral angle PTM. This is peripheral angle PTM. This is equals to 90 degrees in its size according to what is given as the equation. And peripheral angle PTM subtend on chord PM. Again, peripheral angle PTM subtend on chord PM. So here we can implement rule 5. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN, that is a right angle. It is equal to 90 degrees in its size, and therefore peripheral angle MAN, according to this rule 5, must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing we have peripheral angle PTM that is equal to 90 degrees in its size, and therefore according to rule 5 it must subtend on the diameter of the circle. Peripheral angle PTM subtend on chord PM, and therefore according to rule 5 chord PM must be the diameter of the circle. So I write it down. We should find out that chord PM is the diameter of this circle according to rule 5. It is given us the question that point O is the center of this circle. Point O is the center of the circle. Point B is the point on the circle itself. Therefore, OB is the radius of this circle. OB in total equals to OS, that is 2, plus SB, that is 1. So in total, OB equals to 2 plus 1, that is 3. So we should find out that the radius of this circle is equal to 3 units in its length. That is to say, the radius OP equals to 3, and the radius OM must be also equal to 3 units in its length. In the next step, we will do a construction. That is to say, from point S, we will go perpendicular on the diameter PM. Again, from point S, we will go perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other. In the next step, we'll focus on this small right angle OSN. This small right angle OSN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two triangles are similar to each other according to angle similarity rule. That is to say, we prove that the upper right triangle PQO is similar to the lower right triangle OSN according to angle similarity rule. So why those two triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the figures of this upper right triangle PQO are correspondingly equal to all the figures of this lower right triangle, triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the upper right triangle PQO is similar, this is the sense of similar, to the lower right triangle OSN according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle OSN over side PO of the upper right triangle PQO. We can again from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle OSN over side PO of the upper right triangle PQO. SN is the missing side, so we limit as it is. Over PQ. PQ is the line segment that we are looking for in this question. And it is equal to x. We have to find out the value of x. And it is equal to OS. OS equals to 2 units in its length, according to what is given as the question, over PO. PO is the radius of this circle, that is equals to 3 units in its length. So in total, we actually found out that Sn over x equals to 2/3. Here we will multiply this equation by x, and we get that Sn, the missing side Sn, is equal to 2/3 x. Repeat again, we should find out that this is the missing side Sn, that is equal to 2/3 x units in its length. In the next step, we define this angle as beta. And we will focus on this right green triangle, triangle SNM. In this green right triangle SNM, this is angle beta, this angle equals to 90 degrees in its size, and therefore this third missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the big right triangle PTM, this angle equals to beta, therefore angle beta is a common angle that belongs to both triangles. Angle beta belongs to the green triangle, and angle beta belongs to the big right triangle PTM. So in the right big triangle PTM, this angle is beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. According to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to this small right triangle NSM. So why those two right triangles are similar to each other? First of all, this is angle beta, that is the common angle that belongs to both triangles. So we can write down that angle beta equals to itself is the common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So we can prove that all the three angles of this big right triangle PTM are corresponding equal to all those three angles in this green right triangle NSM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PTM is similar to this small green right triangle NSM, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green small triangle SNM over side PT of the big right triangle PTM equals to side SM of the green small triangle SNM over side PM of the big right triangle PTM. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the small right triangle NSM over side PT of the big right triangle PTM is equal to side SM of the green right triangle NSM over side PM of the big right triangle PTM. We have already found out that SN equals to 2/3 x over PT. PT equals to a units in its length according to our definition, and it is equals to SM. SM is the missing side, so we leave it as it is, over PM. PM is the diameter of this circle. The radius is 3, therefore the diameter is 6. So PM equals to 6. So in total, if you found out that 2/3 x over A equals to SM over 6. Here we of course multiply this equation, and we get that according to equation 1. Two-thirds x times 6 equals to ASM. So in this end of equation 1, we have 6 over 3 is 2, and 2 times 2x is 4x. So in total, of this equation 1, we have 2x. So according to equation 1, 2x equals to ASM. So at the now, if we found out that according to equation 1, ASM equals to 4x. rule 15 and we'll implement rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So in the drawing we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OD equals to AO times OB equals to CO times OD. So we can implement rule 15 in our drawing. Because in our drawing we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement here rule 15. So I write it down. If you found out that chord TM, this is chord TM, intersects with chord AB at point S. The intersection point occurs at point S. So according to rule 15, the following equation will be true, that TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. And again, according to rule 15, the following equation is true, that TS times SM equals to AS times SB. This will be equation 2. TS is A times SM. SM is the missing side, so we leave it as it is. And it is equals to AS. AS in total equals to AO plus OS. So AS equals to AO. AO is the radius of this circle, is equals to 3. Plus OS is 2. So in total AS equals to 3 plus 2, that is 5. AS equals to 5 units in its length. Times SB. SB equals to 1 unit in its length. So in total, if you found out that according to equation 2, A times SM equals to 5 times 1. 5 times 1 is 5. So according to equation 2, if you found out that A times SM equals to 5. This is according to equation 2. And according to equation 1, we already found out that A times SM equals to 4x. So we have two different equations for the expression ASM. Therefore, we get equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. Okay, again, equation 3 says that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times Sm according to equation 1 equals to 4x, and it must be equal to A times Sm according to equation 2. A times Sm according to equation 2 equals to 5. So in total according to equation 3, we found out that 4x equals to 5. Here we will divide this equation 3 by 4, and finally we get that x equals to 5 quarters. 5 quarters is 1.25 units. So if we found out that the length of this line 7pq that is equals to x, it is equal to either 5 quarters units in its length, or in terms of numbers, the length of this line 7pq that is equals to x is equal to 1.25 units in its length. So pq is equals to x, it is equal to either 5 quarters or 1.25 units in its length. That is the answer to the second question. In the next step, I'll summarize the lecture. I'll start with the first question, of course. In the first question, our task is to find out the area of this green shape. So in the moment we have a circle inside this big semicircle. We know that this is line segment AQ, that is equals to 4 units in its length. This is line segment TB, that is equals to 1 unit in its length. This is angle PQA, that is a right angle. This is angle STB, that is also a right angle. Again, our task is to find out the area of this green shape. So first of all, we define the radius of this big semicircle as x, and the radius of this small circle is y. Likewise, we define the center of this small circle, this point is point O. We define the center of this big semicircle, this point is point C. In addition, we define the point of tendency of tangent AB with this small circle, this point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle, this point is point H, and we define the point of tendency of tangent ST with this small circle, this point is point L, and we define the touching point of the small circle with the big semicircle, this point is point K. We know that AB is the diameter of the semicircle, therefore it must be twice as long as the radius. The radius of the semicircle is x, therefore the diameter AB must be equal to 2x. So for one side, the diameter AB equals to 2x, but for the other side, the diameter AB also equals to AQ plus QT plus TB again. The diameter AB in total equals to AQ plus QT plus TB. Again, the diameter AB equals to, from one side to x, and from the other side is equal to AQ plus QT plus TB. AQ is 4, QT is 2y, and TB is 1. Again, AQ is 4, QT is 2y, and TB is 1. So in total 2x equals to 4 plus 2y plus 1. So 2x equals to 2y, and 4 plus 1 is 5. So in total 2x equals to 2y plus 5. Here subtract 2y from this equation, and find out that 2x plus 2y equals to 5. Here we took 2 out as a second factor from those expressions, so inside the brackets we have x minus y. So in total we found out that 2 times x minus y equals to 5. Here we divided this equation by 2, and found out that x minus y equals to 5 over 2. 5 over 2 is 2.5. What is the length of this line segment CN? From the moment it is very easy to see that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. Okay, again, we found out that CN in total equals to CB minus NT minus TB. So CN equals to CB. CB is the radius of this semicircle, this equals to x. NT is y, and TB is 1. And again, CB is x, and T is y, and TB is 1. So in total, if you found out that Cn equals to x minus y minus 1. X minus y is 2.5. So we substitute x minus y by 2.5. So in total, Cn equals to 2.5 minus 1. 2.5 minus 1 is 1.5. So in total, if you found out that the length of this line 70n is equal to 1.5 units in its length. We have in the drawing an internal notch between the small circle and the big semicircle. That is to say, they touch each other internally at this point K. Whenever you have an internal notch between two circles or semicircles, you can implement rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their circles together must pass for their touching points. So in the drawing we have two circles. The center of this big circle is 0.0. The center of this small circle is 0.m. The straight line that connects their circles together is of course the straight line OM. And this straight line OM must pass for point P, that is their touching point. Again, according to this rule 9, the straight line OM must pass for their touching point, that is point P. Or OMP is one straight line. Again, OMP is one straight line according to this one, rule 9. So we can implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between the small circle and the big semicircle at point K. Therefore, we can implement rule 9. The center of this big semicircle is 0 at point C. The center of this small circle is 0 at point O. The straight line that connects the circles together is of course the straight line CO. And the straight line CO, according to rule 9, must pass for their touching point, that is point K. Again, the straight line CO must pass for point K, that is their touching point. Or COK is one straight line. Again, COK is one straight line according to rule 9. So if COK is one straight line, it means that CO must be equal to CK minus OK. CO must be equal to CK minus OK. So CO equals to CK. CK is the radius of the semicircle, that is x, minus OK. OK is the radius of this small circle, that is y. So in total, we actually found out that CO equals to x minus y. This is line 7 CO, that equals to x minus y, which in its length. But we already found out that x minus y equals to 2.5. CO equals to x minus y, therefore CO equals to 2.5. Okay. In the next step, we implemented the Pythagoras theorem on this right triangle, triangle CON. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CON that according to the original drawing. In this right triangle CON, OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25, and it is equals to ON squared. ON is y, therefore ON squared is y squared, plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, that is 2.25. So in total, we actually found out that 6.25 equals to y squared plus 2.25. Here we subtracted 2.25 from this equation, and we found out that 6.25 minus 2.25 is 4. So 4 equals to y squared. Here we took out of this equation, and we found out that y equals to the square root of 4, that is 2. So if you found out that the radius of the small circle, y equals to 2 units in its length. We already found out that x minus y equals to 2.5. But y is 2, so x minus y is x minus 2, that is equal to 2.5. Here we added 2 to this equation, and we found out that x equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2. So the radius of the big semicircle equals to either 9 over 2 units in its length, or in terms of numbers, it is equals to 4.5 units in its length. Our test is to find out the area of this green shape. The area of the green shape must be equal to the area of the big semicircle minus the area of the small circle. Again, the area of this green shape must be equal to the area of the big semicircle minus the area of the small circle. And again, the area of the green shape must be equal to the area of the big semicircle minus the area of the small circle. What is the area of the big semicircle? The radius of the big semicircle is x, therefore the area must be equal to pi x squared over 2 minus the area of the circle. The radius of the circle is y, therefore the area of the small circle must be equal to pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total this expression pi x squared over 2 equals to pi over 2 times 9 over 2 squared minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So in total this expression equals to 4 pi. We open the brackets of this expression and found out that pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total this expression equals to 81 pi over 2 times 4, minus 4 pi. So it is 81 pi over 2 times 4. 2 times 4 is 8. So in total, if you found out that the area of the big semicircle equals to 81 pi over 8 square units in its size. We have here minus 4 pi. So we multiplied minus 4 pi by 8 and then we divided by 8 in order to come out of this number. So minus 4 pi times 8 is minus 32 pi over 8. 81 pi minus 32 pi equals to 49 pi. So in total, if you found out that the area of the green shape equals to either 49 pi over 8 square units in its size, or in terms of numbers, it is equals to 19.24 square units in its size. And again, if you found out that the area of this green shape equals to either 49 pi over 8 square units in its size, or in terms of numbers, it is equals to 19.24 square units in its size. So finish with the second question, and with the first question. In the next step, I presented to you the second question, and we answered on the second question of this lecture. In the second question, our task is to find out the length of this line segment PQ that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of the semicircle. Line segment OS is equals to 2 units in its length. This is line segment SB that is equals to 1 unit in its length. This is angle PQB, that is a right angle. This is angle PTS, that is also a right angle. We also know that PT equals to TS. So if we define the length of PT is A, then the length of TS must also equal to A because they are equal to each other. So in the first step, we completed the semicircle to a circle, and we extended 970s by side line until it touches the circle. We define the touching point of the extended 970s with this circle. This point is point M. And we join points P and M together by side line. By doing all those constructions, we can add here peripheral PTM. This is peripheral PTM. That is equals to 90 degrees in size according to what is given in the question, and peripheral PTM subtend on chord PM. So we can implement rule 5. According to rule 5, any peripheral that is equals to 90 degrees in size, exactly like this peripheral PTM, must subtend on the diameter of the circle. Therefore, peripheral PTM that is equals to 90 degrees in size must subtend on the diameter of the circle. Peripheral PTM subtend on chord PM, and therefore chord PM must be the diameter of the circle according to rule 5. Again, chord PM must be the diameter of the circle according to rule 5. In the next step, so PM is the diameter, point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle. OB in total equals to OS, that is 2, plus SB, that is 1. So in total, OB equals to 2 plus 1, that is 5. That is 2 plus 1, that is 3. So the diameter of OB equals to 3 units in its length. Therefore, so the radius OB equals to 3 units in its length. The radius OP also equals to 3 units in its length, and the radius OM also equals to 3 units in its length. From point S, we do perpendicular on the diameter PM. Again, in the next step, we did a construction, that is to say, from point S, we do perpendicular on the diameter PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. In the next step, we focused on this right small triangle OSN. In this right small triangle OSN, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in a triangle. Likewise, in this upper right triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the same rule that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that the upper right triangle PQO is similar to the right lower triangle ONS. So those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we prove that all the figures of this upper right triangle PQO are correspondingly equal to all the figures of this right lower triangle ONS. And therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, if we found out that the upper right triangle PQO is similar, this is the sum of similar to the right lower triangle OSN according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side SN of the lower right triangle OSN over side PQ of the upper right triangle PQO is equal to side OS of the lower right triangle OSN over side PO of the upper right triangle PQO. Repeat again, we derive that SN over PO equals to OS, SN over PQ equals to OS over PO. SN is the missing side, so we leave it as it is. PQ equals to X, that is the line segment that we are looking for in this question. OS equals to 2 units in its length, and PO is the radius of the circle, that is equals to 3 units in its length. So in total, if you found out that Sn over X equals to 2/3. Here we multiply this equation by X and finally found out that Sn equals to 2/3 X. This is line segment Sn, that is equal to 2/3 X. In the next step, we define this angle as beta, and we focus on the green right triangle SNB. In the green right triangle SNB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle PTM, this angle equals to beta, therefore angle beta is the common angle that belongs to both triangles. This angle equals to beta, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the big right triangle PTM is similar to the green right triangle SNM. So why those two right triangles are similar to each other? First of all, this is angle beta, that is the common angle that belongs to both triangles. So we can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, therefore they are equal to each other. So we prove that all the figures of this big right triangle PTM are correspondingly equal to all those figures of the green right triangle SNM. And therefore those two right triangles are similar to each other according to angle similarity rule. Repeat again, if you found out that the big right triangle PTM is similar, this is the sign of similar, to the right small green triangle NSM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the green triangle NSM over side PT of the big right triangle PTM is equal to side SM is equal to side SM of the green right triangle SNM over side PM of the big right triangle PTM. Okay, again we derive that SN over PT equals to SM over PM. we have already found out that Sn equals to 2/3 x over pt. Pt is A, and it is equal to Sm. Sm is the missing side, so we leave it as it is, over Pm. Pm is the diameter of the circle, that is equal to 6. It is twice as long as the radius. The radius is 3, therefore the diameter must be 6. So in total, we should find out that 2/3 x over A equals to Sm over 6. Here we cross multiply this equation 1, and we found out that 2/3 x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. It's 4x. So in total, in this side of the equation 1, we have 4x, so 4x equals to ASM. So according to equation 1, according to equation 1, we actually found out that ASM equals to 4x. In the next step, we implemented rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. In the drawing, we have a circle. This is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule 15 in our drawing. Why? Because in our drawing we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. Because again, we found out that in our original drawing, chord TM intersects with chord AB at point S. So we can implement rule 15. According to rule 15, the following equation is true, that Ts times Sm equals to As times Sv. Again, Ts times Sm equals to As times Sv. But again, according to rule 15, the following equation is true, that Ts times Sm equals to As times Sv. Ts equals to A, Sm is the missing side, so we leave it as it is. So in this side of equation 2, we have ASM, and it is equal to AS. AS in total equals to AO, that is the radius of the circle that is 3, plus OS that is 2. So in total, AS equals to 3 plus 2, that is 5. SB equals to 1. Okay, again, we found out that AS equals to 5 and SB equals to 1. So in total, we found out that according to equation 2, A times SM equals to 5 times 1. 5 times 1 is 5. So in total, according to equation 2, we found out that A times SM equals to 5. This is according to equation 2, and according to equation 1, we have already found out that A times Sm equals to 4x. So we have two different equations for the expression ASM. Therefore, we created equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. And again, equation 3 states that A times Sm A times Sm according to equation 1 must be equal to A times Sm according to equation 2. A times Sm according to equation 1 is 4x, and it must be equal to A times Sm according to equation 2. A times Sm according to equation 2 is 5. So in total, according to equation 3, we actually found out that 4x equals to 5. Here we divided this equation 3 by 4, and we found out that x equals to 5 quarters. 5 quarters is 1.25. So if you found out that the length of this line segment PQ that is equal to x, the length of this line segment PQ that is equal to x, it is equal to either 5 quarters units in its length, or in terms of numbers, the length of this line segment PQ that is equal to x is equal to 1.25 units in its length. Okay, thank you very much.